Welcome to part 3. Let's tackle the dreaded block-on-block friction. A 2 kg block rests on an 8 kg block with a static friction coefficient of 0.5. The floor is smooth. What is the maximum force F on the bottom block so they move together? Let's draw it. A smooth horizontal floor, the 8 kg block on the bottom, the 2 kg block on top. A force F pulls the bottom block and both accelerate together. The standard trap, drawing separate free body diagrams, equating the friction to the pseudo force on the top block and solving a mess of simultaneous equations. This eats up your exam time. Here is your 30-second A-max limit hack. The maximum shared acceleration is strictly dictated by the top block slipping limit, mu s times g. Acceleration max is simply 0.5 times 10, which is 5 meters per second squared. Now treat both blocks as one system. Total force is total mass 10 times 5. That instantly gives us 50 newtons. Option C is our correct answer. Just find the top block's max acceleration and multiply by the total mass. Moving to question 2, the slipping condition. A 4 kg block sits on a 5 kg block. Kinetic friction is 0.2. A 36 Newton force pulls the top block. Find the bottom block's acceleration. Let's sketch the system, the smooth floor, the 5 kg bottom block and the 4 kg top block. We pull the top block with 36 newtons, causing it to slip forward. The standard textbook trap, checking slip conditions, drawing two complex free body diagrams and balancing opposing friction vectors. It's a massive time sink. Here's the 30-second friction driver hack. Once the top block slips, the only forward force driving the bottom block is the kinetic friction transferred from the top block. So the bottom block's acceleration is simply mu k times mass top times g, all divided by mass bottom. That's 0.2 times 4 times 10 over 5. This simplifies perfectly to 8 over 5, which is 1.6 meters per second squared. Option B is correct. Identify the driver, divide the mass and secure your marks.
Question 3 is the classic spring snapping problem. A 2 kg block hangs from a string and a 3 kg block hangs below it from a spring. If the top string is cut, what is the initial acceleration of the 2 kg block? Let's visualize the ceiling, the string, the 2 kg top block, the coiled spring and the 3 kg bottom block. Suddenly the string is cut. The standard textbook trap, calculating the spring constant, drawing new free body diagrams for the exact millisecond and setting up restoring force equations. It's too slow. Here is your 30-second spring memory hack. A spring remembers its force instantly, but a string loses tension immediately. Before the cut, the spring supported the 3 kg block, so its downward pull is 30 newtons. When the string vanishes, the 2 kg block feels its own 20 newton weight plus the 30 newton spring pull. Total downward force is 50 newtons. Divide by its 2 kg mass and you get 25 meters per second squared. Option C is correct. Remember, springs hold, strings snap.
Question 4 introduces variable mass. Sand drops vertically onto a conveyor belt at a rate of 0.5 kgs per second. To keep the belt moving at a constant 2 meters per second, what extra external force is required? Let's animate this. We have a horizontal conveyor belt moving to the right at a constant 2 meters per second, while sand steadily falls vertically onto it. The standard trap, students see the phrase constant speed, assume acceleration is 0, use F equals ma and wrongly conclude the required force is 0. Here is your 30-second mass rate formula. When speed is constant but mass is changing, force is simply the velocity multiplied by the rate of mass change. Let's calculate. Force equals 2 meters per second times the mass rate of 0.5. 2 times half instantly gives us exactly 1 Newton. Option B is correct. Never fall for the zero acceleration trap when mass is dropping. Multiply V by dm by dt and move on. Question 5 tackles rocket propulsion. A rocket burns fuel at 40 kilograms per second with an exhaust velocity of 5 times 10 to the power of 3 meters per second. What is the upward thrust? Let's sketch the launch. The rocket accelerates upwards while the hot exhaust gases are blasted downwards at a massive velocity. The textbook trap, writing out the full variable mass momentum integral, separating mass and velocity differentials and getting lost in the calculus. Here is your 30-second thrust direct multiplier. For any rocket or water jet, the thrust force is instantly the relative exhaust velocity times the rate of mass change. Let's plug the numbers in. Thrust equals 5000 times 40. 5 times 4 is 20 plus 4 zeros. That gives exactly 2 times 10 to the power of 5 newtons. Option E is correct. Multiply exhaust speed by mass rate and secure your marks.
Question 6 covers 2D explosion vectors. A 3 kilogram bomb at rest explodes into 3 pieces. Two 1 kilogram pieces fly off at right angles, both at 30 meters per second. What is the speed of the third piece? Let's visualize the explosion. Boom! One piece flies right, the second flies straight up. The third piece must fly off diagonally in the exact opposite direction to balance them. The standard textbook trap: setting up complex x and y axis momentum equations, squaring both sides and adding them together. A massive algebra trap. Here is your 30-second Pythagoras momentum hack. The momentum of the third piece perfectly equals the vector hypotenuse of the first two pieces. Momentum 1 and 2 are both 1 times 30, which is 30. The hypotenuse is the square root of 30 squared plus 30 squared, giving 30 root 2. Since the third piece is exactly 1 kilogram, its velocity is simply 30 root 2. Option B is correct. Skip the coordinate axis, use Pythagoras for right-angled explosions and save your time.
Question 7 covers 1D recoil straight from the NCERT textbook. A 0.02 kilogram shell is fired from a 100 kilogram gun with a muzzle speed of 80 meters per second. What is the recoil speed of the gun? Let's draw it. The massive 100 kilogram gun recoils backward while the tiny 0.02 kilogram shell blasts forward at 80 meters per second. The textbook trap: setting up the formal conservation of momentum equation, worrying about positive and negative velocity signs and cross-multiplying fractions. Here is your 30-second inverse mass ratio hack. Since the momentum is equal and opposite, the gun speed is simply the bullet speed scaled down by the mass ratio. Recoil velocity equals 80 times 0.02 over 100. That's 1.6 divided by 100. This instantly gives us 0.016 meters per second. Option A is correct. Scale by the mass ratio and save your exam time. Question 8. A classic 2D impulse problem. A 0.05 kg billiard ball strikes a wall at an angle of 30 degrees to the normal and rebounds at the same speed of 6 meters per second. What is the impulse imparted to the wall? Let's animate the bounce. The vertical wall, the incoming ball striking at 30 degrees and rebounding symmetrically. The horizontal velocity reverses, but the vertical velocity stays exactly the same. The standard textbook trap: resolving both initial and final velocities into sine and cosine components, carefully managing negative signs and performing vector subtraction. It's a prime spot for silly mistakes. Here is your 30-second wall reflection rule. Because the vertical component never changes, the parallel impulse is exactly 0. We strictly care about the perpendicular bounce. The net impulse is simply 2 times mass times velocity times cosine theta. Plugging in our values: 2 times 0.05 times 6 times cosine 30 degrees. That's 0.6 times root 3 over 2, which simplifies perfectly to 0.3 root 3 Newton seconds. Option C is correct. Just double the normal component and save your time.
Welcome to question 9. Connected bodies with a massive rope. A block of mass m is pulled by a uniform rope of mass m using force F. Find the tension exactly at the rope's midpoint. Let's draw the system. A horizontal surface, the block m, attached to a thick rope of mass m. A force F pulls it to the right, and we need the tension right here at the dashed midpoint. The standard textbook trap: setting up a linear mass density lambda, taking a small element dx and integrating the tension using calculus. It takes way too long. Here is your 30-second pulling ratio hack. Treat the rope like 2 separate discrete blocks. The tension at any point is simply the total force times the mass behind that point divided by the total mass. At the midpoint, the mass behind the dashed line is the block m plus exactly half the rope, m over 2. The total mass is just m plus m. So the tension is F times m plus m by 2 all over m plus m. Option B is correct. Skip the calculus, treat it as connected blocks and grab your marks.
Welcome to our final question for this chapter. A car accelerates uniformly at root 3g on a horizontal road. A pendulum hangs from its ceiling. What angle phi does it make with the vertical? Let's draw the system. The car accelerates forward, which causes a pseudo force to push the pendulum bob backward, making an angle phi with the dashed vertical line. The standard textbook trap: drawing a complex free body diagram, breaking the string tension into sine and cosine components, balancing them with mass times acceleration and gravity, and dividing the two equations. Here is your 30-second effective gravity hack. The pendulum instantly aligns with the vector resultant of the downward gravity and the backward pseudo acceleration. This forms a simple right-angled triangle where tan phi is exactly equal to the pseudo acceleration divided by g. So tan phi equals root 3g over g. The g's cancel out, leaving tan phi equals root 3. That means phi is exactly 60 degrees. Option D is correct. Draw the acceleration triangle and secure your final marks. If you found this visual breakdown helpful, you need to put that knowledge to the test right now. Head over to neetapp.in or download the NEET app today. We have chapter-wise, concept-wise and level-wise MCQs from easy to moderate to hard waiting for you to master. Plus, you can take free full syllabus mock tests, grab premium NCERT aligned study materials and enroll in our ultimate NEET crash course to supercharge your prep. Don't just watch physics, conquer it. Hit that subscribe button, click the link in the description and I'll see you in the next video.